Isaac Newton discovered a powerful method in algebra, a way to expand 1 plus x raised to any power, even fractions and negative numbers, into an infinite series. But here is the crazy part. Newton never actually proved it for fractions. He just noticed the pattern. It wasn't until 100 years later that Leonhard Euler proved it. And his trick? He didn't use complicated continuous calculus. He defined a functional equation that establishes the equality mathematically. Let me show you how he did it. We all know how to raise something to the power of 2 or 3. You just multiply the brackets. It's simple algebra. But how do you expand 1 plus x to the half power? You can't multiply a bracket by itself half a time. Our basic intuition no longer applies. Newton found this infinite series for the coefficients. If n is an integer, the terms eventually become 0 and the series terminates. But if n is a fraction, it goes on forever. Euler decided to treat this infinite series as a function with respect to n. Let's call it f of n. Our one and only goal right now is to prove that this f of n is exactly equal to 1 plus x to the power of n for any rational number. Euler's approach was to ask, what is the product when you multiply f of m and f of n together? Imagine multiplying two polynomials with infinite terms. This seems complicated. But if you systematically group them by the powers of x, a mathematical pattern continually emerges in the coefficients. For example, the x squared term is the sum of products of earlier terms. In general, the coefficient of x to the power of k becomes a clear summation of combinations. Euler evaluated this coefficient using Vandermon's identity. It is a combinatorial identity. Consider choosing a subset of k items from two disjoint sets of sizes m and n. The summation calculates all combinations of picking j items from the first set and the remaining k minus j items from the second set. It must equal the total number of ways to pick k items directly from the union of both sets, m plus n. Because the coefficients matched term by term, the multiplication simplified cleanly. F of m times f of n is exactly equal to f of m plus n. Through this brilliant deduction, Euler successfully established his powerful functional equation. Now, let's substitute the number 1 into our series. F of 1 simplifies to exactly 1 plus x. Using our new addition rule, f of 2 is just f of 1 times f of 1, which is 1 plus x squared. This establishes that f of n equals 1 plus x to the power of n for all positive integers. But what about any positive fraction? Assume p and q are positive integers. By our rule, multiplying f of p over q by itself q times equals f of p. Since p is an integer, we already know f of p is 1 plus x to the power of p. So f of p over q to the power of q is 1 plus x to the power of p. Take the qth root of both sides, and we find f of p over q is exactly 1 plus x to the power of p over q. Newton's infinite series is proven for all fractions. We can even do negative numbers. F of n times f of negative n gives f of 0. If you substitute 0 into the series, every term becomes 0 except the 1, so f of 0 is 1. This means f of negative n is simply 1 divided by f of n, which is 1 plus x to the negative n. Proof complete. But Euler didn't stop there. He took the limit definition of e to the power of x as n goes to infinity and substituted it into his newly proven binomial theorem. As n approaches infinity, the fractional terms, like n minus 1 over n, simply converge to 1. The expansion simplifies significantly, leaving us with the famous infinite series for e to the x. Euler's algebraic method gives us a clear proof. While Euler's proof was brilliant, he didn't formally prove it holds true for all real numbers. Niels Henrik Abel finally proved its exact convergence limit years later, but we will talk about that in another video. If you want to master the art of mathematical logic like Euler, make sure to like and subscribe to Matilda Academy. I'll see you in the next one.